TCP has been at the core of internet communication for the last 40 years, and in this video, I'm going to show you why. Hello everyone, this is Ed Harmouche. Welcome to another lesson in the TCP and UDP Masterclass. This lesson is the keystone lesson. In this lesson, we're going to show you exactly how TCP works. Now, in the last lesson, we unpacked TCP as it compares to UDP. We talked through all the different things that TCP is said to be able to do. If you want a definition of what each of these things are, I would recommend you check out the last lesson. In this lesson, we're going to show you exactly how TCP does all of these things. That's going to let us explore the TCP header in more detail. Now, I have broken up all the main ideas you need to understand about TCP into 12 simple, distinct ideas. And if you can follow me through these 12 ideas, then you'll be able to say that you understand TCP better than most. Discussing these 12 ideas will have us explore some of the fields inside the TCP header. Specifically, we're going to be looking at these three fields, the sequence number, the acknowledgement number, and the window or the window size, and these four flags, the A, R, S, and F flags. To illustrate all of these, we're going to be simulating a TCP connection between Alice and Bob. The setup for this is that Alice and Bob are computers that are running software, some sort of application, and that application has just given to TCP a bunch of bytes, a bunch of data that needs to be sent to the other side. And with that as our starting point, let's get into the first idea of TCP, which is to define the sequence number and acknowledgement number. The sequence number is a number that is going to be used to track the bytes that are sent, and the acknowledgement number is a number that is going to be used to track the bytes that are received. So let me show you how that works. Let's say Alice shoots a packet over to Bob. She's going to add to that packet a sequence number of 101. That's going to exist inside the TCP header of that packet. In order to confirm reception of that packet, Bob is going to send another packet with an acknowledgement number of 102. The only way Bob could have sent 102 is if Bob had received 101. If Alice had started with something like 501, then Bob would have had to send 502 to confirm reception of this particular packet. Upon receiving this acknowledgement, this tells Alice that Bob definitely received this first packet, which will now allow Alice to send the next packet, which is going to be labeled with sequence 102. Then Bob, to confirm receiving this packet, will send another acknowledgement, this time including the number 103 in the acknowledgement number field. This will prove to Alice that this packet was received. And Alice will continue sending another packet, this time labeling it with sequence 103, which will allow Bob to confirm reception of that packet by acknowledging it with an acknowledgement number of 104. So that is the basic premise behind the sequence number and the acknowledgement number. Notice that the sequence number is tracking what is sent, and the acknowledgement number is tracking what is received. Idea number 2 about TCP is going to further refine our understanding of sequence number and acknowledgement numbers. You see, sequence number and acknowledgement numbers are not actually a measure of packets sent. They're actually a measure of bytes sent or received. So these numbers that we use over here aren't technically accurate. I was just using those numbers to simplify the definition of sequence numbers tracking what is sent and acknowledgement numbers tracking what is received. More accurately would be numbers like this. Alice's first packet is going to include a sequence number, in this case 1001, and it's going to include 200 bytes of data included in that segment. Upon receiving this packet, Bob will confirm reception of that packet by sending acknowledgement number 1201. 1201 is what's going to acknowledge receiving the 200 bytes starting from sequence number 1001. Once Alice gets this, she can then send the next segment. This segment is going to start at sequence number 1201 and also include 200 bytes. And as you can imagine, Bob will then confirm reception of this by sending acknowledgement number 1401. This will now prompt Alice to send the next segment. This next segment is going to start, as Bob expected, at sequence number 1401. This particular segment only includes 100 bytes, which means Bob, to acknowledge receiving those 100 bytes, will send an acknowledgement number of 1501. Understanding the way the sequence number and acknowledgement numbers work is actually very important and a critical component of TCP. So I want to focus on this just a little bit further. This will help us later on when we're trying to understand idea 7, 9, and 11 later on in this video. Notice that if you add the sequence number to the number of bytes, that'll tell you the acknowledgement number required to acknowledge reception of that segment. 1001 plus 200 equals 1201, and that's what Bob used to confirm reception of this segment. Notice that is also the starting sequence number that the sender is going to use for the next data packet. Again, 1001 plus 200 is going to equal 1201. You'll see this again in the next exchange between Alice and Bob. Notice 1201 plus 200 is going to equal 1401, which is the acknowledgement number Bob used to confirm reception of this segment, and the sequence number that Alice is going to use for the next data packet. Now let's explore that exchange a little bit further, because I really want to drive this point home. Inside this segment sent by Alice is 200 bytes of data, and to represent them we'll use these rectangles. Every one of these rectangles represents a single byte. So these would be the first 5 bytes in the set of 200, and these would be the last 5 bytes in the set of 200. The first byte in that set is going to be labeled with the sequence number that was inside the TCP header. And every byte that follows can be identified as an addition to that sequence number. Meaning the second byte in that packet is byte 1202, and the third byte in that packet is byte 1203. And the 199th byte in that packet is byte 1399, and the 200th byte in that packet is byte 1400. When Bob then sends ACK 1401, what he's saying is I have received everything before byte 1401. Or said another way, Bob is saying I am now ready for the next byte that you send me, and that byte should be starting with sequence 1401. And that indeed is the sequence number that Alice is going to use for the next data packet that she sends. So you see TCP actually tracks everything sent on a byte by byte basis. And it's going to use sequence numbers to track the bytes that are sent and acknowledgement numbers to track the bytes that are received. That takes care of unpacking the definition and operation of sequence number and acknowledgement number. Idea number 3 about TCP has to do with how TCP handles situations where packets are dropped on the wire between Alice and Bob. The way it works is every time TCP sends something, it's going to keep a copy of what was sent in cache for a duration known as the retransmission timeout. Then, if an acknowledgement is not received for the segment that was sent, the segment is simply going to be resent. Here's how that works. Let's say Alice sends a segment to Bob, starting with sequence number 1501 and including 200 bytes. As she sends this, she's going to keep a copy of that packet in cache and start the retransmission timeout. If Bob receives this packet, Bob will send an acknowledgement of ACK 1701, and if Alice receives that acknowledgement, then she can simply delete what she had in cache because she knows that Bob received it. She no longer has to keep track of those bytes since Bob definitely got it on the other side. That will then prompt Alice to send the next set of packets, and let's just say something happens on the wire with this packet and doesn't actually make it to Bob. Well, once again, Alice kept a copy of that packet in cache and started that retransmission timeout. And since Bob never received this packet, Bob can never actually send an acknowledgement, which means inevitably this timer is going to expire. And once it does, Alice will realize that she hasn't received an acknowledgement for this set of bytes, so she'll go ahead and retransmit that packet. She can do this because she kept a copy of that packet in cache. This packet, notice, is identical to the packet that was sent earlier. It's starting from sequence number 1701 and includes the same 200 bytes. And let's just say, for the sake of this example, that this packet actually makes it through to Bob. Bob's going to return with an acknowledgement of 1901, and this tells Alice that those 200 bytes have been received, and therefore she can erase this information from cache, knowing that those 200 bytes actually made it over to Bob. So that is how TCP handles situations where packets are dropped on the wire. Now, the cool part about how this works is that it works if packets are dropped in either direction. We simulated this packet being dropped sent from Alice to Bob. Well, let's just say that packet actually made it through, and Bob's acknowledgement is what was dropped on the other direction. Well, in the end, the same situation would occur. Alice sent something and never received an acknowledgement for what she sent, so she's simply going to retransmit. Bob, having received both of these segments, will know that they both start from sequence number 1701 and both include 200 bytes. So Bob will know that this is actually a duplicate of what was sent before. And since Bob knows that this is a duplicate of what was sent before, Bob isn't going to try and keep 2 copies of the same set of bytes. Instead, this sort of clues Bob in to something must have happened to the acknowledgement he had sent earlier. And he'll simply respond by sending the exact same acknowledgement, ACK 1901. So you can see that this system of retransmission timeout and keeping the packet in cache handles packets being dropped in either direction. And that takes care of discussing idea number 3 about TCP. Idea number 4 has to do with how often the receiver has to acknowledge what is received. Initially, with TCP, the receiver was sending an acknowledgement for every single segment received. The issue with that is that effectively doubles the amount of packets that need to be put on the wire. Meaning if Alice sent 100 packets to Bob, Bob would have to send 100 acknowledgements for each of those packets. To reduce that burden, an optimization was added to TCP known as delayed acknowledgement, which allows the receiver to acknowledge every other received packet. Here's how that works. Alice is going to shoot off a packet to Bob. This packet includes 200 bytes and starts with sequence number 1001. Then Alice is going to shoot off another packet to Bob. Now, having received both of these packets, Bob is going to acknowledge both of them by sending this acknowledgement number. Acknowledgement number 1401 says I've received everything before 1401, which includes the 400 bytes that was just sent by Alice. Notice that the acknowledgement number is cumulative. This single acknowledgement is going to acknowledge both of these packets, and really everything before 1401. Upon receiving this acknowledgement, Alice will then send the next two packets in the sequence. Both of these are 100 byte packets for this example, and Bob will confirm receiving both of those with a single acknowledgement acknowledging 1601, which is going to include these two packets. Again, if we take the last sequence number sent by Alice and add the number of bytes, that will get us the next acknowledgement number that Bob is going to use to confirm reception of these two packets. But what happens if Alice has an odd number of packets that she's going to send? I mean, she sent 2 here and Bob acknowledged. She sent 2 here and Bob acknowledged. What if this is the last 200 bytes that she means to send? Bob will never receive a second packet and therefore never send that last acknowledgement. Well, lucky for us, the folks that created the delayed acknowledgement RFC accounted for the situation, and they said that an acknowledgement is going to be sent every other packet or no more than 500 milliseconds from the last packet. This way, if there's an odd number of packets, the acknowledgement will still come. Bob, after waiting the 500 milliseconds for a potential second packet, will then send this acknowledgement number confirming he received these 200 bytes. So that is idea number 4, known as delayed acknowledgements. Idea number 5 is related, but sort of from the other perspective. So I actually want to show them both to you on the same screen to clearly identify how they are different from each other. Idea number 4 was a governance on how often the receiver, Bob in this case, was sending acknowledgements. Whereas idea number 5 has to do with how much data the sender can send before it must wait to receive an acknowledgement number. Idea number 5 has to do with the window size. The window size sets a limit on how much data can be sent before the sender has to stop and wait for an acknowledgement. The window size is something set by the receiver. So in our example, Bob is the receiver, and Bob sets his receive window size of 500 bytes, which means Alice can only send 500 bytes at a time before she has to stop and wait for an acknowledgement from Bob. Now, how Alice knows that Bob had set a window size of 500 is something we'll talk about in idea number 6, but for now, simply take it as fact that Alice knows the window size for this connection is 500. In any case, Alice sends off the first packet, and this first packet includes 200 bytes, which means Alice can now send only another 300 bytes before she has to stop and wait for an acknowledgement. So Alice then sends the next segment, which also includes another 200 bytes, which is going to reduce how many more bytes Alice can send to 100. And now, if Alice has another 200 byte packet that she means to send, she cannot, because the window size wouldn't account for it. She can, however, send a 100 byte packet, which would reduce her remaining window size down to 0, where she'll finally have to stop and wait to receive an acknowledgement from Bob. The concept of a window size is sometimes referred to as bytes in flight. Notice, 500 bytes is how many bytes can exist on the wire in the path between Alice and Bob before they get acknowledged by the other side. That is the idea behind bytes in flight. In any case, upon receiving these 500 bytes, Bob is going to confirm receiving those 500 bytes by sending a single acknowledgement number. In this case, acknowledgement 1501. Remember, acknowledgements are cumulative, so 1501 would confirm the reception of all 500 of these bytes. That is going to now reset Alice's window size back to the max, which is 500, and now Alice can continue sending data to Bob. So again, her first next packet is 200 bytes, reducing her window size to 300. Another 200 bytes reduces it to 100, and then finally another 100 byte reduces it to 0, and now she has to stop and again wait for another acknowledgement from Bob, which is going to show up with acknowledgement 2001. That is the idea behind the window size. Understand how it's different from idea number 4 and delayed acknowledgements. The window size is referring to how much data the sender can send, whereas delayed acknowledgements has to do with how often the receiver is sending acknowledgements. Now, normally, Bob would indeed be trying to send an acknowledgement after every second packet, but for the sake of this illustration and showing you idea number 5, I skipped that part of TCP. Which brings us back to a question that we asked earlier. Bob set his receive window at 500 bytes, but how did Alice know what that receive window was? Well, that has to do with idea number 6. Idea number 6 is that the window size is actually sent in every single segment. Remember that the window size is actually a field in the TCP header, so every TCP segment sent between Alice and Bob includes a window size field, which means these acknowledgements sent by Bob also included the window size that Bob intended to use. But how did Alice know that the window size was 500 before this first acknowledgement sent from Bob? Well, that should be a clue that something had to happen before data was sent between Alice and Bob in order to establish the initial window size. But more on that later. For now, understand that the window size is actually set in every single segment. The additional benefit to the window size being sent in every single segment is it can actually be updated throughout the life of the connection. This is how TCP does what is known as flow control. So let me show you. Let's just say that at this point in the conversation, Bob is receiving too much data too quickly. Bob still wants to confirm having received those 500 bytes, but wants to slow down how much data Alice is sending at a time. Well, what Bob can do is send ACK 1501 to confirm receiving these 500 bytes, but then also send the window size, which exists in each segment, of 0. This is instantly going to reduce Alice's send window size to 0 and force her to stop sending data until Bob sends another acknowledgement number. Bob can use this time to process the data he just received from Alice, or more than likely process all the other data he might be receiving from other people connecting to Bob at this exact same time. Then, once Bob has caught up, you could say, he can then send another acknowledgement indicating he is now ready for more data. Notice the acknowledgement number is the same. Well, that makes sense because Bob hasn't received any more data in between those two acknowledgement numbers. And notice Bob now increases the window size to 600. Maybe he's cleared out a lot of information in the backlog and is ready for more data. Upon receiving this acknowledgement number and window size update to 600, Alice can now send 600 bytes of data before she has to stop and wait for another acknowledgement. So Alice can now continue sending data to Bob. She'll send 200 bytes, then another 200 bytes, then another 200 bytes, and Bob will confirm receiving those 600 bytes by sending ACK 2101. Notice in addition, Bob changed the window size now to 500. That's the benefit of the window size being set in every single segment, is the receiver can fine-tune the window so that he's always receiving at the optimal rate. That is idea number 6, and that is how TCP does what's known as flow control. Okay, we're at the halfway point. Do you fully understand ideas 1 through 6 that we just covered? Make sure you do, because everything we cover going forward is just going to build upon what we've already learned. With that said, to understand idea number 7, I want to pull back a sequence of exchanges that we looked at earlier in this video. So far in this lesson, we've been looking at Alice as the sender and Bob as the receiver. Specifically, we've been looking at Alice's sequence numbers tracking what she has sent, and Bob's acknowledgement numbers tracking what he has received. But TCP is actually bidirectional, which means both parties can send data to each other, which means both parties actually have a sequence number, and both parties actually have an acknowledgement number. So it's not just that Alice uses a sequence number to track what she has sent, and Bob using an acknowledgement to tracking what he has received. It's also that Bob has his own sequence number, independent from Alice, to track what Bob sends to Alice, and Alice has her own acknowledgement number to track what she has received from Bob. With idea number 7 in mind, let me show you what the exchange would look like. Alice is going to start by sending this packet. This packet starts with sequence number 1001 and includes 200 bytes. Notice Alice has an acknowledgement that she is including in this packet, and how she knows to start at 3001 will be answered in the next idea. In any case, to acknowledge receiving this segment, Bob is going to respond with this acknowledgement. ACK 1201 is going to confirm the reception of the 200 bytes starting with sequence number 1001. But notice, in this segment, Bob is also including 300 bytes of his own that he is trying to send to Alice. And if we apply what we learned before, sequence number 3001 plus 300 equals 3301, and that'll be both the next sequence number that Bob starts with or the acknowledgement number that Alice used to confirm receiving these 300 bytes. In our illustration, Bob is going to send the next packet, and notice that it's going to start at 3301, just as we deduced. This packet also includes 300 bytes, so if we do 3301 plus 300, that gets us 3601, and that indeed will be how Alice will acknowledge receiving these 600 bytes. Her next segment is going to include acknowledgement 3601. But it's also going to include 200 bytes of data. And her sequence number is going to start at 1201, which is both what Bob has been acknowledging and is expecting as the next sequence number, and the result if we add 1001 plus 200. So with this one segment, Alice is both acknowledging what she just received from Bob and sending another 200 bytes. What comes next is something from Alice in this example, and notice it's going to start at sequence number 1401, which is what you would get if you added 1201 plus 200, and this is also going to include another 200 bytes. So if we did 1401 plus 200, we should expect sequence number 1601 is the next thing that Alice sends, or acknowledgement 1601 is the next acknowledgement that Bob will send. And that's what we have here. Notice in this acknowledgement, Bob is sending 0 bytes. Remember we talked about delayed acknowledgement back in idea number 4. Well, Bob just received 2 segments and now has to send an acknowledgement to confirm having received these 2 segments. That is why you have a 0 byte acknowledgement, and this happens with TCP all the time. Next, Alice is going to send another data packet, another 200 bytes, and as expected, that's going to start with sequence number 1601. That is the idea behind number 7, that TCP is bidirectional. Both parties can send data, therefore both parties have their own independent sequence numbers that is used to track what they send. Now, I do want to point out a couple of things. Notice here, Bob is sending 2 segments in a row with the exact same acknowledgement. That makes sense because in between these 2 segments, Alice hasn't sent any new data. So in either case of these 2 segments, the last received byte was 1200, and Bob is confirming that he is now ready for 1201. You'll notice the same thing occur over here when Alice is acknowledging 3601 twice in a row, because again, she hasn't received anything new from Bob. Understanding how sequence numbers and acknowledgement numbers track with each other is very important. And if you're going to be doing any sort of TCP troubleshooting, you have to have this skill. So I'm going to highlight the conversation from only one direction. Here, you're looking at the numbers of Alice's sequence number and Bob's acknowledgement numbers. And what you'll notice is that these are actually the exact same sequence and acknowledgement numbers we've looked at in ideas 1 through 6. Now, all we've done is also added Bob's side of the conversation to our illustration. And Bob, just like Alice, had his own sequence numbers that he's using to track what he has sent, and Alice is using her own acknowledgement numbers to track what she has received. That is the concept behind idea number 7. Now, there's still a question that we haven't answered. How did Alice know to start at acknowledgement 3001? Well, that actually brings us to idea number 8. Idea number 8 has to do with the starting sequence number, also known as the initial sequence number or the ISN. And the way it works in TCP is each sender is going to randomly choose their own sequence number. So for this illustration, Alice chose an ISN of 1000 and Bob chose an ISN of 3000. But how do they know each other's starting point if they each picked it independently? These initial sequence numbers have to be shared before data can actually be exchanged between Bob and Alice. And that's what brings us to how TCP connections are established and what's known as the three-way handshake. The core purpose of the three-way handshake is to exchange these initial sequence numbers. And that's what actually brings us to idea number 9, which is how this conversation even started. Every TCP conversation starts with what's known as a three-way handshake. But inside a three-way handshake, 4 different events are occurring. And I want to start by highlighting each of those 4 events. In our example, Alice is going to initiate this TCP connection, but it could happen in the other direction as well. So Alice is going to start by sending a synchronized request to Bob. This is where Alice picks an initial sequence number randomly and shares it with Bob. In our illustration, she's sharing a sequence number of X. Bob is then going to confirm receiving that synchronized request by sending an acknowledgement number of X plus 1. This is how Alice knows that Bob definitely received her initial SYN, because Bob can only send X plus 1 if he received X. But of course, as we just covered, TCP is bidirectional. So Bob also needs to pick an initial sequence number and share that with Alice. And that's what happens next. Bob picks an initial sequence number, in this case Y, and sends a synchronized request to Alice. And Alice, predictably, will respond with an acknowledgement saying she has received Bob's synchronized request by responding with Y plus 1. Again, the only way for Alice to send Y plus 1 is if she had received Y. So that's how Bob knows that Alice had indeed received Y. Now notice these 2 middle events are both sent from Bob to Alice. And the fields that each of these events use inside the TCP header don't actually overlap. So both of those actually end up happening in the exact same packet. And that is where you get a 3-way handshake of SYN, SYN-ACK, and an ACK. It's actually a SYN and an ACK in one direction, and a SYN and an ACK in the other direction. So now that we've mapped out the 4 events that occur in the 3-way handshake, I want to show you how the actual sequence numbers and acknowledgement numbers are going to look like on a TCP header for the simulated conversation we're having between Alice and Bob. It's going to start with Alice's SYN packet that looks like this. She's going to include a sequence number of 1000, that is the randomly selected initial sequence number that she picked for this conversation. She's going to include that right here. We know that this is an initial sequence number because the SYN flag is turned on. She's also going to include an acknowledgement number because it's built into the TCP header. It has to be there. But notice she's simply going to include all zeros. Since the acknowledgement flag is turned off, this acknowledgement field can actually be ignored. It's an irrelevant value, which makes sense because at this point she has no idea the ISN that Bob is going to pick. Upon receiving this, Bob is going to send his SYN-ACK, and the SYN-ACK will look like this. The acknowledgement field will include 1001. This is where Bob is acknowledging receiving Alice's sequence number plus 1. Notice the acknowledgement flag is also turned on. Now, this field is actually relevant and should be paid attention to. Bob is also going to include his own initial sequence number. He randomly chose 3000 for this connection. And we know it's an initial sequence number because the SYN flag is turned on. Upon receiving this guy, Alice is then going to confirm receiving it by sending this segment. This segment has sequence number 1001, which is exactly what Bob was expecting next. And Alice is going to include an acknowledgement number of 3001, this time with the ACK flag turned on, indicating this field is now relevant. And this is how Bob knows that Alice definitely received his SYN request because she is sending Y plus 1 or 3001. So that is what the TCP header would look like in a TCP 3-way handshake. But now I want to draw your attention to another field in the TCP header, specifically the window size field. Remember I told you the receiver sets the window size in each connection. Well, since TCP is bidirectional, both Alice and Bob are technically the receiver at some point in the connection. And in these initial packets, they are each sending what they want to start with as their initial window size. It doesn't have to be the same between the SYN and the ACK, both sent by Alice. It can totally be different, but this is how they both know the starting window size values, and then they can adjust them dynamically as they need to throughout the rest of the connection. Now, before we move on to the next idea, there's something else I want to draw your attention to insofar as these sequence numbers and acknowledgement numbers. Earlier in this lesson, I told you you can always add the sequence number plus the number of bytes to see the next sequence number sent by the same sender. But notice over here, 1000 plus 0 doesn't equal 1001. So what's actually going on? Well, the whole way that TCP works to acknowledge receiving something is by essentially sending what was received plus 1. And so Bob, in order to acknowledge receiving this synchronize, has to send the synchronize plus 1. That is why Bob is sending 1001, and that is why Alice is starting with 1001. Now this is sometimes referred to as the phantom byte, because even though no data bytes have been sent in that packet, it did bump the sequence number forward once. This phantom byte phenomenon is actually going to happen one more time within the TCP connection, and we'll explain it when we get to idea 11. But for now, I just want to drop it in your head as a teaser. With that said, that takes care of covering the TCP three-way handshake and our idea number 9. So if we bring back the rest of the data exchange that we've been looking at between Alice and Bob, we have the three-way handshake that absolutely started this exchange of data between Alice and Bob. Now, since our illustration is now accounting for flags, I do want to mention in every data exchange packet following, the ACK flag is turned on. And that makes sense because in all cases, the acknowledgement flag is indicating that the acknowledgement field is important and it's acknowledging the last packet received by either sender. What you'll notice is in a TCP connection, the only segment sent without the ACK flag turned on is the initial SYN by the initiator of the TCP connection, in this case Alice. And that makes sense because at this point, Alice has no idea what Bob's initial sequence number is going to be, so this field is entirely irrelevant. In any case, at this point, I've shown you how a connection starts with the three-way handshake, and I've also shown you the middle portion of the connection, which is the data exchange portion of a connection between Alice and Bob. All that's left to do is to show you how a connection ends. And that actually brings us to idea number 10. Idea number 10 is that there are two ways for TCP to close a connection. And to properly show them to you, we're going to again use the TCP header. The first way the TCP can close a connection is what I'm going to call the graceful method. The graceful method uses FIN or finished flags. And the second way is what I'm going to call the ungraceful method. And the ungraceful method uses the R or the reset flag. Idea number 10 is that TCP has two ways to close a TCP connection. And idea 11 and 12 will explore each of those ways in more detail. Idea number 11 is what I refer to as the graceful connection closing. This is what happens when everything went well. Meaning Alice and Bob started a conversation successfully, exchanged data successfully, and once they have both sent and received exactly what they meant to send and receive, they can now close the conversation and go about their day. There are 4 things that actually occur inside a graceful connection closing sequence. I'm going to show them each to you. You'll notice that this will follow a similar sequence to the three-way handshake. Now, it doesn't matter who initiates this. In our example, it's going to be Alice, but it can absolutely be initiated from either party. In any case, this is how it works. One side will send to the other. In our example, Alice is sending to Bob that she has finished sending data. She'll include her last sequence number of X. Bob will then acknowledge receiving that FIN flag by acknowledging X plus 1, this number plus 1. Bob will then have to close the connection from his side, so Bob will then send a finished flag of his own and also include his last sequence number of Y, and predictably Alice will confirm receiving that by sending an acknowledgement of Y plus 1. So the 4-way closure is a FIN and ACK in one side and a FIN and ACK in the other side. And just like in the three-way handshake, these two events sometimes occur in the same packet, but not always, and you'll see what I mean shortly. Now let me actually show you what this would look like to close out the simulated connection that we are using between Alice and Bob. Alice is going to start by sending a FIN segment, and in that FIN segment, Alice is going to include her final sequence number of 1601. Notice that is the sequence number that Bob was expecting her to send next. Bob will then respond by sending an ACK of 1602. Notice it's going to be X plus 1. Alice's X in this case was 1601, and therefore Bob is going to acknowledge receiving 1601 and the FIN flag by sending 1602. Then Bob is going to close the connection from his side. He's going to say, I have finished sending data. My final sequence number is going to be 3601, and then Alice will confirm receiving that by acknowledging with 3602. Now, some of you might be asking yourself, how come Bob didn't just include the FIN flag there? Well, Bob absolutely could have, but I intentionally illustrated it this way to show you an important point about how TCP closes connections. You see, these 4 events don't have to happen sequentially. It's very possible that Alice might finish sending data well before Bob might finish sending data, or vice versa. For example, what if this segment right over here, which included 200 bytes, was Alice asking for another file, and possibly the last file she meant to get from Bob? Maybe the 200 bytes included something like, give me file a.jpg. Once Bob acknowledged it, if that's the last file that Alice was going to ask for from Bob, she can go ahead and send her FIN right now. She is done sending data. There are no more files that she needs to request. But of course, Bob has to actually send the file before he is done with his side of the communication. So you see, it's very common for TCP connection closures to happen many packets apart. And that is why I intentionally illustrated them as 4 different packets. Of course, if Bob has more to send at this point, that's going to change the sequence and acknowledgement numbers for our final FIN and ACKs. So let's continue the conversation, and then I'll show you how these will be updated. So again, we can use what we've used before. Sequence number plus number of bytes equals the next sequence number that's going to be sent. Notice here, 3601 plus 0, that equals 3601, and that's going to be the next data segment that Bob's going to send. This particular segment has 100 bytes, so if we do 100 plus 3601, we would get 3701, which is the sequence number for the next thing Bob sends. And at this point, Alice has received 2 data packets from Bob, so she now has to send her acknowledgement to tell Bob that those packets have been received. Notice that even though Alice finished sending data, that doesn't preclude her from sending acknowledgements. Bob still wants reliability to everything he has to send. So Alice still has to follow all the rules for acknowledgements that we covered before. Her ACK 3801 is confirming the reception of these 200 bytes. Now, for the sake of the illustration, and for the fact that I don't have much more screen real estate, let's just say that this is the last thing that Bob meant to send to Alice. Well, now, Bob is done sending traffic to Alice, and now Bob can go through his side of the connection closing sequence. So Bob's FIN is going to include his last sequence number of 3801. And notice that is exactly what Alice was expecting to see next from Bob, 3801. Bob's acknowledgement number is 1602. Notice it hasn't changed since Alice sent her last packet that needed to be acknowledged. No new data has arrived from Alice, therefore Bob's acknowledgement number has stayed the same. Upon receiving this FIN, Alice will respond with this. Notice the acknowledgement number is Bob's final sequence number plus 1, as we just discussed, and her sequence number is still 1602 because again, she hasn't sent anything new since she closed her connection. So that is how TCP closes a connection when everything went right, when the data exchange went according to plan. Earlier, when we talked about the 3-way handshake, I told you about this phantom byte. And some of you might have recognized the phantom byte happen in this screen right now. Notice, Alice sent this packet over here, which included 0 bytes. And if we follow the rules that we talked about earlier, sequence number plus number of bytes should equal the next sequence number that she sent. But even though this was 0 bytes, it did bump the sequence number forward 1. This is crucial because this is how Bob is able to acknowledge having received that FIN. Okay, so why do we even do this phantom byte thing? Well, to answer that, I want to point you to these 2 acknowledgements sent by Bob. If we didn't bump the sequence number forward, and therefore the correlating acknowledgement number forward, on FIN flags and also SYN flags from the 3-way handshake, you'd have a situation where both of these acknowledgements would end up looking identical. Notice, if we didn't bump the sequence number forward, this would be ACK 1601 still, which is the same as it was before. And Alice would have no way of knowing whether Bob is simply resending this acknowledgement or actually acknowledging the new significant segment that she just sent. That is why the FIN flags and also the SYN flags bump the sequence number forward, even though those segments don't actually carry any data. And so that wraps up our discussion on idea number 11, which was the graceful connection closure mechanism using FIN flags. Which brings us to idea number 12, the last idea in this lesson, and that is what I call the ungraceful connection closing mechanism. If idea 11 is how a TCP connection closes when everything went right, idea 12 is what happens when something went wrong. This is what I'm calling the ungraceful connection closing mechanism. And it happens with a simple one-way message, which includes the reset flag. Consider a situation where something weird happened with the sequence numbers and the acknowledgement numbers. Or possibly one of these two TCP speakers received something that they weren't expecting. Well, in those cases, TCP needs a way to ejection seat out of that particular connection. And that's where the reset flag comes into play. The way it works is any party can send a reset flag to the other, and that indicates that something went wrong and the connection needs to close. It doesn't matter which party sends the reset. As soon as a reset is sent, that party will forget everything about the TCP connection, and as soon as somebody receives the reset, that party will also forget everything about that particular TCP connection. The rules of sequence numbers and acknowledgements still have to apply though, so if, in our example, Alice decides to send the reset at this point, her reset is going to include the sequence number that Bob is expecting. As soon as she sends this, she is now going to delete everything she knows about that TCP connection. And Bob, as soon as he receives it, is also going to delete everything he knows about the TCP connection. Notice, the reset does not need to be acknowledged. But for the sake of thoroughness, I'm going to show you what the reset would look like if Bob had sent it here instead of Alice. And as expected, it's going to follow the same rules for sequence numbers and acknowledgement numbers that we discussed throughout this lesson. Bob's last sequence number was 3601 and didn't include any new data. Therefore, the next packet he's going to send is also going to start at 3601. And since it includes this reset flag, the connection is instantly terminated. Notice, again, it does not have to be acknowledged. It's simply a quick exit from this particular TCP conversation. If Alice and Bob still need to exchange data with each other, then they'll start a new TCP conversation and the entire process will start all over. And that is idea number 12. So that's it. That's the core of TCP in 12 distinct ideas. And if you followed me through each of those 12 ideas, then you can say you understand TCP better than most. But what's next? Where do we go from here? Well, there's 3 places we can go. First, at the end of the last video where I compared TCP and UDP, I teased some additional topics that we could cover regarding TCP. TCP is actually a pretty fascinating protocol, and there is so much more to it than merely what we covered in the last 2 videos. If you want me to finish this series and create the full TCP Masterclass, then I need you to help me blow up these videos. I'll set a reasonable goal. If we hit 100K views in the next 6 months, then I'll commit to creating the full TCP Masterclass. And who knows, maybe that could also lead into a series on Quick. Second, if you enjoyed how I teach in this video and want a comprehensive series to understand computer networking, then there's no better place than my Networking Fundamentals series. You can check that out here. Finally, third, and announcing for the first time officially, I've decided to turn my Networking Fundamentals series into a full networking course. This is going to be the premier, vendor-agnostic, job-agnostic computer networking course. It's going to be wrapped around the practical understanding of computer networking that the entire tech industry is expecting you to have right now. Whether you're aiming for software development, or network engineering, or cybersecurity, any job in tech, it all requires you to understand computer networking. Let's face it, everything is connected to the internet these days, and understanding how that works will be what sets you apart professionally. There'll be more details about the full course in the first comment of this video. Otherwise, that is all I have for you in this video. I hope you got a lot out of this TCP deep dive. Thank you for watching, and we'll see you in the next video.